In this video I'm going to take you through how I solve the problem of my shop vac, which I use in the shed to clean up sawdust and chips off the floor. How I solve the problem of it filling the vacuum bags.
This is my shop vacuum cleaner, which I can fill a bag of sawdust in about 5 minutes.
Now my solution was to make a cyclonic dust extractor. So the first thing I'm going to do is just quickly go through what a cyclonic dust extractor does and how it looks, and to do that we're just going to quickly look at a animation I saw of dust particles running through a cyclonic dust extractor. So what's actually happening there is there's an air pump source connected to the top of the funnel, which isn't obvious in this animation, and basically that air pump source creates a low pressure inside the funnel. So the top right hand side of the funnel is open to the source of dust, usually a hose or a vacuum hose of some sort, so that the dust comes in. It comes in from the top right, and it hits the circular wall of the funnel and begins to spiral into the funnel, and because gravity is applying, it spirals in and down. And as you can see, it eventually spirals around the walls and out the bottom of the funnel.
And this is my paint can dust extractor that I made, so that the dust actually ends up going in the bin at the bottom, and inside that paint tin is a cyclone funnel. So the whole unit ends up being a cyclone dust extractor. And in the tub you get all of your large stuff, and then the small dust particles go into the vacuum cleaner. With the hoses disconnected, now we'll just have a look inside the lid, which we take off. I've just used 50mm plumbing fittings, and you can see inside the lid, you can see where this pipe comes in and the dust runs at a tangent. It runs around the outside, and then it drops down through the funnel, which is in the bottom of the paint can. So the paint can is actually attached to the lower drum via a couple of MDF donuts. So they're rings that I've made out of MDF. Just to adapt the difference in diameter.
Here I'd just like to quickly talk about how we actually made the funnel. The reason I'm doing this bit is because it's actually interesting in the form of mathematics and a bit of geometry.
Okay, so the dimensions of the funnel are as shown on the blackboard here in yellow. So the smaller diameter of the funnel is 100mm. That was nominal because it basically matches the diameter of the biggest vacuum hose I've got, and it's an easy number to work with. The internal diameter of the paint can is 222 millimeters, and 2/3 of the vertical height of the paint can is 170. So our funnel is going to fit into that yellow trapezoid. So to make the maths work and the geometry work on this, you'll see I've put in a centre line. The centre line allows me to work with triangles, which is really important. As you can see, I've extended the yellow line on the right so that it intersects the side of the paint tin, that's here, and it intersects the centre line of the paint tin, that's around about here. Okay, you can see now that we end up with a right angle triangle using the centre line. Using the centre line, the line at 170 mils from the bottom, and the diagonal line that joins those two. As you can see, I worked all of this stuff out on paper before I sort of went anywhere with it. The main thing to note off my workings is that I actually ended up drawing this to scale to be able to get that extension past the bottom of the paint can, so that I could actually do my mathematics on the triangle. When I was doing this, I actually ended up just drawing it out in full size on graph paper, and I ended up with that vertical dimension, which was the centre line extending past the base. That vertical dimension was 300, which means that if the vertical dimension is 310 and we know the bottom of the paint can is at 170, well, that line extends 140 past the bottom of the paint tin. You'll see where we use that 140 a little bit later to calculate part of the funnel. Now we do a little bit of geometry. We've got sides A, B and C there, and you might have seen that equation before, a squared plus b squared equals c squared. So we need to actually calculate the diagonal side C, so it works something like this. Alright, so when you do the mathematics, it's 310 squared plus 111 squared equals c squared, and it all ends up looking something like 329.3 millimeters, which we're going to call 330. Now the next important measure is the small triangle, which is made up of this area here. Now we know some of those dimensions already, so that is 50 there, and we know that that dimension is 140. So once again we've got to solve the equation for C. Okay, so when we do the arithmetic for this, it looks something like this. A squared plus b squared equals c squared. It's 140 squared plus 50 squared equals c squared, and we end up with a number which is about 148.7 millimeters. We'll call it 149. So you can see there our two main numbers is 149 is the inside diameter measurement of the cone, and 329 is the outside diameter measurement of the cone. Okay, so now you can see that that gives us the diameter of the smallest diameter, which is 149. That gives us the smallest part of the cone, and 329 gives us the largest, or the outside diameter of the cone. So there's one more piece of information we need, and that's how much of the material do we need to actually wrap around. You can see that a small cone with the same height would actually use less material than a large cone with the same height. Now in the case of a cone, the amount of material that you get is determined by the amount of material that you use is determined by, you know, the angle of the whole donut that you can use. So you can see that that would actually be a whole donut if you actually continued it in a circle. So what we're trying to work out now is how many degrees of the donut, or what segment of the donut do we need to make the cone give us our fit our internal paint can. Now we know that the diameter of the internal diameter of the paint can was 222. So what we're going to try and do is some mathematics to give us the circumference of a circle with a diameter of 222. So the circumference of a circle is pi times the diameter of the circle, which is pi times 222, which is 3.1416 times 222, which equals 697 millimeters. So we know that the inside of the circle of the paint can is 697 meters all the way around. Now we've got a circle and the radius of the circle is 329. Okay, so the diameter of the circle is 658. Right, so we're working out the larger circle now. So the circumference of the circle equals pi times d, or 2 times pi times r, because there are two radiuses in one diameter, which equals 2 lots of 3.14 times 329. So that's 2 lots of 1033 equals 2066 millimeters. So to help us work out how many degrees or what segment of the circle we need, we need these two numbers here. The total circle is 2066 millimeters, but we only need 697 of it. So what we need to know is the percentage. Okay, so we're going to work out a percentage, 697 on 2066, and then we're going to apply that percentage to the total number of degrees in a circle, which is 360. So that's what we end up there. That's the arithmetic we're about to do, and that will give us a percentage of the total 360 degrees, and that percentage just happens to work out to 33.74. So 33.74, we're going to apply that to 360 degrees, and if we do that we end up with the magic number of 121.45 degrees. So there's our arithmetic there. So the arc, or the segment of the circle that we need to make our funnel, is 121.45 degrees, with an internal radius of 149 degrees and an external radius of 329, and that will give us our funnel. So what I did in order to make this easy was to cut it out of tin, was I actually made up a template in MDF, which is our MDF template there. I just laid that out on our piece of tin, used a texture marker to mark it out. I allowed a 2 centimeter overlap at the end there, which you can just see the mark, 2 centimeter overlap mark there, and then cut it out, and blow me down if it didn't actually work. Well, it did actually work, and that's why I got blown down.
So
thank you.
Now that we've actually got the segment of tin cut out to match the arc that we calculated, I'll just quickly show you on a scrap how we actually bent it into a funnel. So basically what we're doing is just, as you can see, we rotate the tin a little bit, and then we put a little bit of a curve in it, and a little bit more of a curve in it, and a little bit more of a curve in it, until what happens is we end up with part of a funnel. So you can see that that ends up being part of a funnel. Thanks.
If you take a closer look, you can actually see where the difference in diameter is, and you can see the outlet there for the funnel, and you can also, from the other end, you can see the funnel. Here we have the dust extractor, a couple of bits of MDF that I'd cut out on the bandsaw, and you can see where I've actually cut a slot into the circle. Now that slot has two purposes. One is it allows me to get the blade of the bandsaw to cut the internal circle, but the second thing I did was I actually made the slot some 3 or 4 millimeters wide so that I had some adjustment, and then I've put in a screw, as you can see there, that actually pulls that gap closed once we've actually got the drum inside it, and a little bit of duct tape around the bottom gives us a seal. When you pull that closed, it actually tightens on the duct tape and gives you a fairly good air seal around the bottom there. So first we tighten down the screw to eliminate the gap, and then we do up the fastening screws that fixes one piece of MDF down onto the other. Now in this case we've actually got 4 of these all around the perimeter of the MDF circle. This jig on the bandsaw is the means by which we cut nice accurate circles. Basically what it is a fairly decent piece of MDF. In this case I think it's about 19mm. As you can see, the blade passes part way through it, and then in a line with the blade we've got a number of holes, and each of these holes represents a it represents a radius of a circle that we have to cut out. So the first thing to do is you need a pivot point, and I'm just using a 3mm drill bit that's a bit buggered as my pivot point. And then what we do is we cut ourselves a square of MDF so that from the centre, and then drill a 3mm hole the same size as this drill bit through the centre of the MDF so that it lines up with the appropriate hole. And basically from that hole to the edge of the square that we're going to cut our circle out of is the same distance as from the blade there to the drill bit. Alright, so as you can imagine, if you then stick your square onto that drill bit there, the drill bit acts as a pivot point, and you just rotate the MDF around past the blade, and you end up with a really accurate circle. So it goes something like this. Probably about 4 or 5 kilos of particles off the garage floor, the large stuff, which would normally just end up clogging up the vacuum cleaner bag.